Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you. And this is the DADM, which is Data Analysis and Decision Making course under the NPTEL MOOC series. And if you know, as you know, the course duration is basically for 12 weeks, which is 30 hours. 30 hours basically gets converted into 60 lectures, because each lecture is for half an hour. And each week we have 5 lectures, which is half an hour each. And we are in the 49th lecture, which is basically the last but one lecture for the 10th week. Now, if you remember, in the last lecture, we were basically discussing about the concept of equivalence, that given a decision of a deterministic one, you want to basically balance it with a probabilistic one. And I did use the word of fair gamble, but it need not be a fair gamble, where the corresponding probabilities can be P and 1 minus P. But what I actually meant is that the expected value of the deterministic one, which is technically the certainty value based on which you will try do the calculation and break them into the gamble, would be such that the expected value of the gamble would also be equivalent to this. That means, if the certainty value is C, then the U of C multiplied by 1 is the probability, will be equal to U of W1 into P1 plus U of W2 into 1 minus P1, because 1 minus P1 and P1 are the probabilities, and we can continue doing it and break it into more gambles or reduce them with respect to the expected value and discuss it further. Now, further considering the discussions, utility or decision sciences, the other criteria which can be utilized for ranking are basically geometric mean, safety first criteria and stochastic dominance. So, I will go through them slowly. Now, we generally know for any trying to find out the central characteristics of a distribution, we generally use the mean, the median and the mode. In another mean, we have the geometric mean, the arithmetic mean and the harmonic mean. So, we are trying to basically use the geometric mean for as a tool in order to find out the utilities accruing from any decisions. So, what we mean by geometric mean, what we mean by safety criteria and stochastic dominance, I will basically discuss. Now, for the geometric mean, for the decision maker, consider the maximum geometric mean is the case when the highest probability of reaching or exceeding any given level of wealth is possible in the shortest period of time. So, we will basically try to utilize that value of the functional form of the mean, which is the geometric mean, so that it will give us the highest utility or the highest expected value of the utility. For the decision maker making, considering the maximum geometric mean means would also mean that the highest probability of exceeding any given level over any given period of time would also be possible. So, I am basically trying to utilize the concept of geometric mean in order to consider that what is the highest probability of reaching or exceeding that, and the highest probability of exceeding any given level of wealth. So, there is one given level of wealth, what is the highest probability over and above that, and another case is basically what is the highest value attainable. Based on this, we will take the decision. So, for the utility analysis of the decisions, so consider R I j is the ith possible return on the jth decision, and the probabilities are given as R, and the returns is basically given by I R suffix j v. So, G is basically a returns based on the geometric one, and the J's are basically the suffixes based on which I am trying to consider. So, that is the decision making for which number, and ith is basically possible set of such outcomes inside one decision. So, consider there would be j such decisions, each would basically have I of them under each of this so called decision making. Now, I will consider the values corresponding to the first, second, third, fourth returns for, say for example, the first decision making, second decision making, so on and so forth accordingly. So, what I need to find out is basically the probabilities. So, I will basically add up 1 plus r 1 into j into p 1 into multiply dot dot till 1 plus r into j into p n minus n comma j minus 1, because I am trying to basically find out the probability accordingly. So, p I j's would be the probabilities based on which I will do. So, for each decision the probabilities would basically sum up to 1. So, if I am considering say for example, the jth decision or the first decision, the corresponding probabilities would be p 1 1 for the first case, p 1 1, p 1 2, no p it would be p 1 1, then p 2 1, then p 3 1, p 4 1, so on and so forth, where the first suffix would basically mean the possible returns under that decision making, and the second one would basically imply the decision making which is there. We will choose the maximum probability or the geometric mean value based on which the calculation can be done. Now, consider we have the following combinations of assets of decision making which are considered as A, B, C in the following ratios on the weights to form a portfolio. The returns are 10, 20 and 30 respectively, and in this case this 1, 2, 3 which you have are the decisions, which is j is equal to 1, j is equal to 2 and j is equal to 3. So, under j is equal to 1 you will basically have A, B, C combined in some proportions. Under j is equal to 2 again you will basically have A, B, C combined in certain proportions. Under say for example 3 you will basically have A, B, C combined in certain proportions. So, the proportions based on which you are trying to do the calculation for 1, 2, 3 are basically given along the row. So, it is 20%, 20%, 60% for A, B, C under decision 1. 1/3, 1/3, 1/3 for A, B, C under decision 2, and 0.25, 0.25 and 0.5 which is 25%, 25%, 50% for A, B, C under decision 3. So, the corresponding this values of the returns for the geometric mean would be given as per the norm when we are trying to find out. So, if you remember the returns were given, so these are basically the corresponding probabilities. So, probabilities are given as 20%, 20% and 60%, 33.33 or 1/3, 1/3, 1/3 and the last case being 25, 25 and 50. So, these values are coming as 0.2, 0.2, 0.6 for the first case, 1/3, 1/3, 1/3 for the second case and 0.25, 0.25 and 0.5 for the third case. Now, the returns are basically given for the case of the ABC as 10%, 20% and 30%. So, when you utilize that, the values which you found out for RP1 is 0.237, RP2 which is 0.197 and RP3 is 0.222. Based on that you will be able to rank them accordingly to find out what is the best decision or the choice based on the fact that you are trying to take the geometric mean of the returns for your decision. Now, we basically consider the utility-analysis decision sciences other criteria which is the geometric mean. So, maximizing geometric mean returns is equivalent to maximizing the expected value of the log utility function. So, when you are taking the log utility function, in the same case if you remember we have considered the quadratic utility function and the returns to be normal and they were basically equivalent. In a similar way, if you are trying to basically maximize the geometric returns, it will be equivalent to maximizing the expected value of the log utility function. So, hence if you are trying to take a decision trying to maximize the geometric return in one hand and trying to basically maximize the expected value of the log utility function, they would basically give you the same result, that is an if and only if condition. So, if you use criteria 1 to select and then again to use criteria 2 to select, where criteria 1 is maximizing the geometric return, mean return, and criteria 2 is basically maximizing the expected value of the log utility function. So, both of them would basically give you the same result. In the similar way, when you use the returns to be normal or trying to basically use the quadratic utility functions, in both ways you basically calculate, you will get the same result. So, under the first principle, safety principle, The tenets is that the decision maker is unable or unwilling to consider the utility theory for making his or her decision process. So, here I am basically trying to analyze the decision making under the methodologies for which the person is considering the utility theory is such that it is a safety first criteria comes into the decision making process. So, in this safety first principle criteria, the analysis is like this. In the decision making is because here the utility function will be such that the person considering the utility function would always be very risk averse, in the sense that he is trying to basically take a decision such that he wants to avoid the risk on trying to make the minimum loss. And under this methodology, people will make the decision placing more importance to the bad outcomes. That means, probabilities may be the same for the good and the bad, but they will try to basically analyze the decisions where bad decisions are important for them, based on which they are going to take the decisions which will be effective for them. So, when we are considering the safety first criteria, I did mention the concept that what is RP, RL and RP bar. So, I will basically go into details. Considering you have a decision where the decision is not only of one criteria or only one set. Consider you are taking a decision, and in the sense that the decision is basically for buying the set of stocks or buying a set of projects, whatever it is, or investing in projects. Then RP would be basically a so called portfolio being formed from these decisions, and you want the probability of the portfolio of these decisions to be as less as possible than a fixed values which you have. So, let me draw the diagrams for the first one. So, it will be in the case if this is R1, and consider if RP falls onto the left hand side, consider this. So, let me use a different color. So, it falls on the left hand side, you want to basically minimize this probability, that is all, because less the probability better. If it is on the right hand side, obviously you will try to maximize it, push it as far as possible to the right. In the case of maximizing RL, what we are doing is this. This is RL, push RL to the right hand side as far as possible, such that automatically the concept of trying to minimize the distance between RP and RL onto the left side would be such that RP would also be automatically stretched on or pulled onto the right hand side. So, in the sense that we are trying to basically maximize our overall return. And finally, when I am taking the RP value with a bar, which is the expected value, what is here is basically this, which I did not draw, but I will mark it here with blue colors. So, this is the average value, this is the average value. So, what is happening? This is for the third diagram, this is the average value. So, you are trying to basically push it onto the right hand side. So, one case you are trying to minimize the area between RL and RP, where RP is on the left hand side. The second case is basically trying to push RL on more onto the right, so that automatically RP also moves. And in the third instance is basically you are trying to basically move the average value such that the whole distribution shifts onto the right, because higher returns are on the right hand value. So, consider that if the returns are normally distributed, I am considering returns are normally, remind that, then the optimal portfolio of the decisions would be the one where RL or some threshold was the maximum number of standard deviations which is away from the mean value. So, what you are trying to basically consider is that if the distribution is there with an average value of RP bar and RL is something where some value onto the left hand side, we want to find out that how many such standard deviations RL is from the mean value. So, if I am able to draw I will draw it here. So, even though it is there are a lot of information, but I will draw it here. So, it is easy for. So, this is the value. So, this is the R average RP value, and this is RL. So, I want to find out this is how many such standard deviations into K. So, this K is the number of standard deviations which is there on the left hand side. So, let us consider an example for the minimization of probability of RP less than RL. So, this RP value which I said was on the right hand side, left hand side you want to minimize this area. So, this is RL, this is RP, and this is RP bar. So, let us consider an example for which we try to minimize probability of RP less than RL. Remember, we consider the returns are normally distributed and the suffix p denotes the portfolio, where RL means the fixed level of returns which we have kept as 5. So, some threshold values. So, with RP value being of A, B and C being 10, 14 and 17, then the standard deviations are given for A, B, C as 5, 4, 8, then the difference from the 5% would be, for the case when you are trying to analyze RL which is 5, 5 would be 1 standard deviation, would be so on the left. So, it will be 2.25 standard deviation and it would be 1.5 standard deviation with respect to the values of A, B, C. When we combine them, obviously the portfolio will have a different mean and different standard deviation. So, consider these are not investments only one asset, or there are some portfolios which we are renaming them as A, B, C. So, that does not matter, basically I am trying to get the concept clear. So, when we analyze the safety first criteria, so these are the distributions which we have. This blue color distribution is the normal one, again the green color is the normal one. Only remember one thing, for both the cases the mean values are different, which is fine, because for the green one returns are on an average lower, and for the blue one the returns are on an average higher. So, hence I will use the highlighter. So, this is the average value which is R bar A, this is the average value which is R bar B. Now, what is important is to note down that the standard deviations are different also. So, for B it is much more flatter. So, hence the plus and minus standard deviation, the overall, but the area covered would be the same if you convert them to standard normalized values. So, this is the overall area on the values from minus sigma sigma plus to plus sigma. So, which is for sigma corresponding to B, the B distributions, because that is what the distribution has been drawn for the blue one, and for the red one it is basically minus sigma A to plus sigma A, and obviously it seems to be narrow because it is much more compressed. But when I am trying to find out the corresponding value, how far it is, I would obviously consider that the RP value, let me draw it, RP somewhere here, RP value somewhere here. So, what I will be interested would be like this, if I am considering the case of the green one. So, let me blue one. So, let me use the blue color, it will be easier. So, I will draw it accordingly. So, now let me draw it and try to analyze the areas probabilities. If I consider the blue part, highlight blue. So, I will be most interested to find this area, because that is the area between the RL value and RP value. This is RP. So, I should write it down for better clarification for all. So, this is RP. So, this blue area is the area we want to minimize, and when I want to find out, I have removed it. So, it is easier for me to draw. When I want to find out with respect to the green one, because the distributions are same for two different portfolio decisions. So, it will be now be this area. So, the areas would be different and minimization would happen based on the area being covered. So, if I expand this, I think I will be able to give a better picture. Let me try to draw. So, this would be the first is there the black line, which is this one, then is the RL value, then is the blue line. I am just drawing this left portion, then is the green line, then is the RL value. So, what I have drawn is this, I expanded this in order to make you understand and mark these values. So, if you pay attention, you can understand. So, this will be RL, this will be RP. So, when I want to find out the area, the green portion would be, first I will draw the green portion. So, this will be the this is the green one. So, corresponding to the green graph of the normal distribution. So, let me first erase it, done. Then I want to basically do it for the blue one. So, the blue one would be this. So, obviously, those areas would be different. So, this is just a way of trying to analyze the decisions. So, we can basically draw it accordingly. Now, in order to determine how many standard deviations RL lies below the mean value, which is RP bar, we calculate RL minus the standard deviation divided by the standard. We are trying to basically normalize them. Normalize them, if you remember, we always use this formula. If it is x, the random variable x minus expected value of x by the standard deviation x, that would be normalized and give you the capital Z, which is the standard normal deviate. Thus, we want to minimize RL less than RP being less than RL. So, obviously, this is being normalized, RL minus RP is the mean value of the return divided by sigma p. So, that would basically also give me maximization. So, if I basically take the minus sign outside, it will be maximization of RP bar minus RL divided by sigma p. So, this would be equivalent to the case that if we replace RL by the risk free interest rate from the bank, it will be RP bar minus RF divided by sigma p. So, what we are doing is that we are considering the normal distribution and trying to find out what is the overall area which is being covered. So, this my apologies. So, initially it was this, then it gets converted into, so this is capital X, small x, capital Z, small z. So, they are just transformation. So, even though for our example, we have simplified assumption by considering only normal distribution, but this was hold true for any distribution having the first and second moments accordingly. So, we can solve the problems accordingly. Now, according to Chebyshev's inequality, so F Chebyshev and Markov inequalities can be also utilized. I will consider that in more details later on. So, according to Chebyshev's inequality, for any random variable having expected value of E x and V x, you can find out the corresponding amount of deviations which you will have or what is the maximum amount of deviation which you will have. So, based on that you can take the decisions likewise. I will explain that in the later class. So, with this I will end this 39th lecture and considering more details further on. I know that I am basically finishing a little bit fast, but only for this portion, because if I try to basically consider that, it will take a little bit more discussions, which I will try to basically keep it in the last class for the 10th lecture. So, it will be much more easier for me to explain and go slowly, such that you also have a feel and in sync into the discussions. And hopefully by the 50th lecture I will finish off the decisions sciences and start continuing. The relevance of this would come out later on when we consider the multivariate distribution and the other cases. Have a nice day and thank you very much for your attention.